we are ready to solve, and as I told in the previous case, it is just pure maths at this stage. Okay. All the physics are discussed, we know the physics behind this ordinary differential equation, which is a Navier-Stokes equation, simplified form of that. We also know the physics behind the boundary condition as well. Okay. They are the no slip boundary conditions. So, just like your maths class, where you would have been given such a ordinary differential equation given the boundary condition. Now, you have got a chance opportunity to derive the governing equation and state the boundary condition as well. We know the physics behind them as well. Okay. Okay. Now, to proceed further, to integrate, you should know that dou p by dou x is a constant, it is a given value. Okay. It is a pressure gradient along the direction of flow. So, let us integrate once, we get dVx by dy is equal to 1 by mu dou p by dou x y plus constant C1. Let us integrate once again, you get Vx is equal to 1 by mu dou p by dou x, and then we have y squared by 2 and then C1 y and then C2. Okay. Now, we will have to evaluate the constants, we will use the boundary conditions. Vx is equal to 0 at y equal to minus h. So, let us substitute in this equation. So, left hand side is 0, right hand side substitute y equal to minus h here. So, it becomes h squared and then we have minus C1 h and then C2. Let us use the second boundary condition, Vx equal to 0 at y equal to plus h. So, left hand side is 0, right hand side once again h squared because it is y squared, and we have plus C1 h and then C2. So, we have two simultaneous equations in the two constants. Okay. So, let us subtract, we will have to eliminate one of the constants. If you subtract, we will eliminate C2, and then if you subtract this equation from this equation, you will have 2 C1 h, and these terms will cancel, which means C1 is equal to 0. And if you substitute either in this equation or in this equation, you will find out C2 as minus 1 by mu dou p by dou x h squared by 2. So, let us substitute back in this equation, Vx is equal to 1 by mu dou p by dou x y squared by 2, and then we substitute the constant which I have found out for C1, which is 0, and then for C2, then if you simplify, you get this equation 1 by 2 mu dou p by dou x into y squared minus h squared, and this velocity profile is parabolic, okay, because it depends on y squared, and such a parabolic velocity profile is shown here. That profile is not at all new to us. We almost from the beginning of the classes we have come across that parabolic velocity profile several times. So, it is very nice now to really derive the velocity profile, the equation which represents this velocity profile. Okay. The equation which determined this parabolic velocity profile is this equation. Of course, at y equal to, if we substitute y equal to minus h plus h, Vx is 0, that is a boundary conditions we have used, and so we have Vx equal to 0 here, Vx is equal to 0 here. Regarding maximum velocity, we will shortly discuss. Okay. What else can be found out from the velocity profile? We can find out what is the volumetric flow rate flowing between the plates. Okay. How do you evaluate that? Let us write the velocity profile which I have derived. Of course, as I discussed, it is a parabolic velocity profile. Now, how do you evaluate the volumetric flow rate? We know volumetric flow rate is velocity into the area. It is this velocity and then this area. Okay. But now, and that is this area is what is shown here, but now the velocity varies along the y direction. So, I cannot take the entire area. What I do is take a small strip of height dy and then find out what is the volumetric flow rate through that small strip and then integrate. Okay. And that is what I have shown here. The volumetric flow rate is dq over that small strip of height dy and the width is of course w. So, volumetric flow rate through that small strip is Vx, the velocity, into the area of the strip which is dy into w, height is dy, width is w. Now, to find out the volumetric flow rate passing through the entire area, we integrate this expression from minus h to plus h. That is the meaning for this expression, q is equal to minus h to plus h Vx dy w. Also like to mention that we have come across similar steps when we discussed an application for integral mass balance, okay, including velocity profile. In fact, we took the same case of flow between two parallel plates which are fixed, and we took a similar velocity profile and found out the inlet flow rate, outlet flow rate, etc., and we had a similar discussion. So, you can refer that discussion as well. Okay. Now, let us evaluate this volumetric flow rate. Just to normalize, what we usually evaluate is q by w, volumetric flow rate per unit width of the plate, and this is the width of the plate. Okay. So, let us do that. Q by w is equal to minus h to plus h. We will substitute for Vx the velocity profile which we have determined, and that is what I have shown here, and w has been taken to the left hand side, and then we have dy. So, let us integrate. If you integrate, you have y cube by 3 minus h squared y. We will substitute the limits minus h and plus h. If you do that, you will get this expression for the volumetric flow rate. Remember, dou p by dou x is negative, that is why I have a negative sign there. Volumetric flow rate has to be positive anyway. So, dou p by dou x is negative. So, this term along with the negative sign is a positive quantity. So, which is 2 by 3 h cubed by mu dou p by dou x, of course minus sign. Okay. That is what I just now told you, pressure decreases in the direction of flow. So, dou p by dou x is less than 0. Okay. Now, what we usually do is this dou p by dou x is a negative quantity. So, we will do a simple variable replacement which is usually followed in fluid mechanics. We take this minus dou p by dou x. What is dou p by dou x? Pressure gradient. Let us take two locations x2 and x1 and the pressure two locations P2 and P1. So, dou p by dou x is P2 minus P1 by x2 minus x1. Let us say you have point 1 here, 2 here, and corresponding x values and then pressure values. Now, we know that pressure will decrease along the direction of flow, which means P2 minus P1 is negative. So, if we include the negative sign, the numerator can be written as P1 minus P2, and that is positive. And so, we write that as delta P, and x2 minus x1 we write it as L. So, what we have done is written minus dou p by dou x as delta P by L, which is a pressure gradient, a constant pressure gradient. What is L? L is the length of the plates, and this is L, this is L. Okay. And now, delta P is positive, we say it as pressure drop, that is P1 minus P2, P1 is higher, P2 is lower. So, delta P is pressure drop, it is a positive value. L is of course the length of the plate. So, delta P by L is the pressure gradient. So, what is given to us is the pressure gradient. Of course, L is based on the length of the plate. So, either you say pressure drop is given or pressure gradient is given. Okay. And this I think we should keep this in mind for further discussion. Dou p by dou x is negative, minus dou p by dou x is represented as delta P by L. Okay. So that moment you look at delta P, it is positive, okay, easy to understand as well. Okay. So, we are writing the expression for flow rate in terms of delta P by L. Look at the advantage, here we had a minus sign dou P by dou x, now it becomes very simple, delta P is positive and minus sign has been accounted for. Now, what is use of this equation? Two ways of looking at it. I have been always telling that we are given the pressure gradient. Okay. So, if the pressure gradient is given, or putting it the other way, if you tell the allowable pressure drop, then I can calculate what is the flow rate that can be pumped, flow rate per unit width. Okay. Other way, if you tell me that I need to pump so much of liquid between the plates Q by W, then you can calculate what is the required pressure drop. That is more practical as well. That will determine the rating of the pump. Should you use if you give some flow rate, you can determine should you use whether a half HP pump or 1 HP pump. Okay. So, we will determine the capacity of the pump or rating of the pump. Okay. Those are the practical applications. We can also find out the average velocity and maximum velocity. Let us do that. So, this is the flow rate per unit width, which I derived in the previous slide. How do you define average velocity? The volumetric flow rate divided by the cross sectional area. Okay. So, let us do that. Vx average is equal to the flow rate divided by the cross sectional area. What is the cross sectional area? 2h into W, that is this cross sectional area, and we have got expression for Q by W, and that is this expression, and then divide by 2h, and this is the expression for the average velocity. We have been looking at the profile. We know Vx varies along y, but suppose you want to represent as an average velocity, then this is the expression, okay, h squared by 3 mu delta P by L. Okay. Now, we can also find expression for the maximum velocity, which happens at y equal to 0, okay. And how do you find out? In the expression which I have derived for the velocity distribution, for the velocity profile, substitute y equal to 0, and then you get 1 by 2 mu, and this minus sign has been combined with this dou P by dou x to give you delta P by L, and of course, you have h squared. Okay. And you can also find out the ratio of this maximum velocity to the average velocity, which is 3 by 2. Okay. So, the maximum is 1.5 times the average velocity. As I told you, all these calculations, velocity profile and then volumetric flow rate, average velocity, maximum velocity, all can be analogously done for flow through circular pipe. To restrict, to make it easy for us and then restrict to Cartesian coordinates, we are deriving it for flow between parallel plates. Okay. We can also derive the pressure distribution. Let us do that. Dou P by dou x is equal to a constant, and I have written that as minus delta P by L. This is what we have seen. We said minus dou P by dou x is equal to delta P by L. I have now written as an expression for dou P by dou x, because we are going to evaluate the pressure distribution. We need expression or values for the pressure gradients along the x, y, z direction. So, that is why I have written this as dou P by dou x is equal to minus delta P by L, and delta P by L is a constant. For example, delta P by L could be, let us say phi, unit of pressure is Newton per meter squared, because we have pressure gradient. For example, could be a value like phi kilonewton per meter cubed. Okay. Now, the pressure gradient in the y direction is hydrostatic. So, it is dou P by dou y is equal to minus rho g, and of course, there is no pressure gradient in the z direction. Of course, pressure varies both in the x and y direction. Remember, in the last case For the case of planar cuvette flow, pressure variation was only in the y direction, there was no pressure variation along the x direction. In this case, pressure varies both along the x direction and the y direction. Okay. So, now how do we proceed? What we are going to do now, the steps we have already seen when we discussed an example after Bernoulli's equation. One of the examples which we discussed after Bernoulli's equation, we derived an expression for the pressure distribution. Okay. What we are going to do now is exactly similar to what we had done earlier. So, I would recommend that you can refer those slides. One of the examples after we the example which we discussed after Bernoulli's equation. Okay. After the irrotational form of Bernoulli equation, we derived Bernoulli's equation both for rotational and irrotational. The example which we discussed after discussing irrotational Bernoulli's equation, the steps there and the steps here are same. Okay. So, let us start with the pressure gradient in the x direction, which is minus delta p by L. Let us integrate. Okay. In fact, the wordings, the variables, the constant are also I have used this same way. Okay. So, if you integrate, we get minus delta p by L into x. Remember, delta p by L is a constant. So, on integration you get minus delta p by L x, and then it is partial integration. So, our constant can be a function of y. So, we denote it as f 1 of y. The same nomenclature has been used earlier also. So, now what should we do? We have to evaluate f 1 of y. So, we will differentiate this equation dou p by dou y. This term will be 0 on differentiation, because partial differentiation with respect to y, and this one, the constant term, it is a function of y, it is a function of y only. So, it becomes total differential. So, that becomes df 1 by dy, and we know that dou p by dou y is equal to minus rho g. So, we are equating to minus rho g. So, df 1 by dy is equal to minus rho g. Now, we will have to find out f 1. So, let us integrate. So, f 1 is equal to integral of df 1 by dy into dy, and what is df 1 by dy? That is minus rho g, which is found out here, and then of course, we have dy. Let us integrate, we get minus rho g y plus a constant. Here it is not a function, because we are this integration is usual integration, it is not partial integration. Now, let us substitute the expression for f 1. We said f 1 is a function of y. Now, we have found out that function. Let us substitute that in this equation, okay, and what we get is this equation, p is equal to minus delta p by L x. For f 1 of y, we have minus rho g y plus c. Now, we will have to evaluate c, the constant. Now, we will have to be given a value of pressure at some point. Let us say at x equal to 0, y equal to 0, we have p equal to p naught. What is that point? This point. Let us say beginning of the channel we denote as x equal to 0, the center line is of course y equal to 0. So, at that point the pressure is p naught. So, let us evaluate the constant. Left hand side p naught, this is 0, this is 0, and then we have c here. Okay. So, 0, 0 and then c. So, the constant is p naught. So, what we have is p is equal to p naught minus rho g y minus delta p by L into x. Remember, delta p by L is greater than 0. So, let us continue with this in the next slide. That is the equation for the pressure distribution. What do we conclude from this? First observation is that pressure varies both along the x direction and the y direction. In the earlier case, there is a pressure variation only in the y direction in the case of planar cuvette flow. Now, we have variation both in the x direction, y direction. Now, let us discuss the y direction, because that is a that arises because of hydrostatic condition, and that term is same as what we have seen earlier. Earlier we had only these two terms P naught minus rho g y, and that is why I am writing that term first. So, pressure decreases along y direction balancing gravitational force. This is same as what we had seen for planar cuvette flow. Now, for Poiseuille flow, pressure decreases along x direction also balancing viscous force, okay. And that is clear from here. We have minus delta p by L into x, delta p by L is positive, remember, okay. So, pressure decreases along y direction balancing gravitational force, there is nothing new, it is same as planar the cuvette flow, but this is something different from the earlier case, pressure decreases along x direction also balancing viscous force, okay. Now, this representation, a very good representation of what we are discussing now from the book by Wilkes, Fluid Mechanics for Chemical Engineers, and of course, it has microfluidics, CFD, COMSOL, multiphysics, etc. Now, let us look at understand the pressure distribution. It shows shear stress distribution that we will see later. For the moment, we will discuss the pressure distribution. Now, first observation is that we know that pressure is compressive. So, it always acts into the control volume, that is why here also it is into the control volume, here also into the control volume, first observation. Second observation, pressure increases with the depth. So, it increases as you go down the y axis, that is why pressure is low here and then high here, because of it is a hydrostatic pressure distribution. Same is the case on the exit also, low here and then high here. So, both the cases pressure increases as you go down the y axis. Now, if you look at this length and this length, the left hand side pressure inlet has a larger length, at the exit has smaller length. What does it mean? It tells about decrease in pressure, okay. And that is of course constant throughout the height, whichever if you take at any position, then there is a decrease in length, the decrease is also constant, continues till the bottom, okay. So, let us quickly repeat, the arrows are towards each other into the control volume because it is compressive, and pressure increases as you go down both at the inlet and the exit, and then in terms of let us say magnitude, the inlet pressure is more, the outlet pressure is less, and that is why that is shown in the length of arrows as well, and that difference is same at any vertical position, okay. Just to get little more understanding, so I have taken some numerical values. Now, as I told you, moment you talk about pressure for incompressible flow, it is relative. So, somewhere we should fix a pressure, okay. We always talk in terms of difference in pressure, okay. So, let us take this pressure as 150 kilopascal. What does it mean? At x equal to 0, y equal to plus h, at that point let us say 150 kilopascal. Now, let us say the distance between the plates is such that the pressure here is 160 kilopascal, it should be increasing. So, let us take there is some 10 kilopascal increase, and because pressure varies linearly with height, at the center line it will be 155 kilopascal. Now, let us come to the exit. Let us say the conditions are such that flow, viscosity, etc. are such that the pressure drop is 5 kilopascal. So, inlet pressure is 150, exit pressure is 145 kilopascal at y equal to h. Now, at the exit also we have seen at any position, any x position, pressure increases if you go down. So, here again at the top it is 145 kilopascal, at the bottom the same 10 kilopascal increase should be there, and that is why this pressure is 155 kilopascal. Once again the pressure variation is linear, and so this pressure is 150 kilopascal. So, at any position if you take, let us say at y equal to plus h, the difference between inlet and outlet is 5 kilopascal. If you take y equal to minus h, the difference between inlet and outlet is 5 kilopascal. Even if you take center line once again it is 5 kilopascal. Okay. So, very good representation, numerical values we are discussing, but the pictorial representation is from the book, a very good representation of pressure distribution. Okay.